Most people don't know this. Right now, you have a perfect solar panel hidden at home. It's not on your roof. It doesn't depend on the sun, it's in your water tank. That container you have on the roof, or that elevated lagoon on the hillside, or even that plastic water tank that feeds your irrigation system. It's a battery of potential energy waiting to be released. Look at this multimeter. 13 volts, half an amp, 5 watts of continuous power, generated only by water falling through gravity. Let's talk about the traditional system that most people know, photovoltaic solar panels. They're incredible, don't get me wrong. They convert sunlight directly into electricity. It's magic of physics, but there's a problem. When a cloud passes, production drops 80% in seconds. When it rains, the panel operates at 10% of its rated capacity. And when night falls, well, production goes to zero, simply disappears. This means you need big, expensive batteries to store energy during the day and use it at night. These batteries degrade, they lose capacity, and they cost 1,500 to 3,000 euros for a minimally decent setup for a house. At night, the problem becomes more obvious. The solar panel is up there on the roof, completely useless. Night is when people are home, using lights, charging phones, running security sensors. But the energy source is switched off. The battery, of course, was supposed to be charged during the day. But if it was a cloudy day, or if you used more energy than expected, the battery dies fast, and now you're without power, without light, without a charger for your phone, without security sensors working. It's a constant compromise. Energy consumption planning. Anxiety about whether there's enough battery left. Another option people consider is the gasoline generator. Internal combustion. Works at night, during the day, whenever you need it. But it has obvious disadvantages. First, the cost of operation. Gasoline isn't free. A 2,000-watt generator running continuously burns through 10 to 15 liters per week. That's about 40 to 60 euros per week in fuel. Second, the noise. A generator operates at about 70 to 80 decibels. For reference, that's equivalent to a conversation in raised tone. If you live near neighbors, they'll love that. Third, maintenance. Combustion engines require oil, filters, spark plugs, periodic cleaning, and you use them only 20% of the time, which speeds up wear because the engine isn't optimized for intermittent operation. Fourth, emissions. Carbon, nitrogen oxides, particulates. Not exactly friendly to the environment. There are also small wind turbines, but those depend on wind, which is just as inconsistent as sun. They work well in some places, in others they're useless. But there's a solution that's literally in plain sight. A solution that works 24 hours a day, 365 days a year, regardless of weather. A solution that cost me 25 euros in recycled components, elevated water. If you have a reservoir, a water tank, a lagoon on a hillside, or even a bathtub on the roof, you have a continuous source of energy. Gravity doesn't fail, water doesn't stop falling, it's predictable, it's consistent, it's liberating. The water falling through gravity has kinetic energy. That energy is immense. If you have 2 meters of height and 10 liters per minute falling, you constantly have 2 watts of available power. That sounds small, but it's continuous. 24 hours. If you have 5 meters of height, you have 25 watts. If you have a hillside with 20 meters of drop, you have 250 watts. An entire house. In this video, I'll show you exactly how to build a micro-hydroelectric turbine that captures that energy and converts it into usable electricity. Electricity you can use to charge phones, power security sensors, light up the garden at night, or continuously recharge batteries. And the best? We'll build this in 4 hours with tools you might already have and materials that cost less than a meal at a restaurant. Let me explain what's really happening here. It's pure physics, but very simple. When you have a volume of elevated water, that water has what we call potential energy. It's energy stored due to position. The higher the water, the more potential energy it has. The formula is E equals mgh, mass times gravity times height. When we release that water and it falls, the potential energy converts into kinetic energy, energy of movement. The water accelerates. Now here's the secret. The higher the reservoir, the longer the water has to accelerate. With 2 meters of height, a drop of water reaches the bottom at about 6 meters per second. With 10 meters, it reaches 14 meters per second. That velocity is everything. Because when that moving water hits a turbine blade, it transfers all its kinetic energy to the blade, making it rotate. The faster the water, the stronger the impact, the faster the wheel spins. It's like the difference between a garden hose connected directly to a faucet versus the same hose falling from a house roof. The falling water has velocity, the faucet water just sprays. Now comes the clever trick. If we just let water fall freely from the bottom of the tube, the energy would disperse. The water would spread out, the impact would be weak and widely distributed. But instead, we use a nozzle, a simple tube with a small orifice at the end. That orifice forces all the water through a tiny opening. What happens? All the kinetic energy of the water concentrates into a thin, powerful jet. It's like the difference between firing a showerhead, scattered water, weak impact, versus putting your finger on the hose tip, concentrated water, strong impact. The orifice size is critical. For 2 meters of height, a 2 to 3 millimeter orifice is perfect. For 5 meters, it would be 1 to 1.5 millimeters. The smaller the orifice, the more concentrated the energy. But the orifice can't be so small that it clogs with debris. That's why many micro-hydroelectrics have a simple filter before the nozzle, a nylon sock, for example. It catches sand or leaves, lets clean water through. That thin jet is what will hit the turbine blades with hammer force. Now that concentrated water jet hits a special wheel called a Pelton wheel. It's a design invented over 150 years ago by an engineer named Lester Pelton, and it's still the best design for this. Each blade on the wheel has a very specific shape. It's concave, like a half moon. This is fundamental. When the jet hits the blade, the water doesn't simply ricochet away. No. The water enters the concavity, the blade embraces the water, and the water follows the blade's curve. The blade redirects all the energy of the jet. While this happens, the water loses almost all of its linear velocity, but that velocity is transferred as rotational torque. The blade has to move out of the water's way. When that happens, the entire wheel rotates. It's nearly perfect energy transfer. With optimized design and correct alignment, you get 85 to 90% efficiency. Compare that to solar panels, which have 20 to 25% efficiency. The wheel then reaches extraordinary rotation speed. With 2 meters of height and a well-directed jet, the wheel can spin at 500 to 1,000 revolutions per minute. With greater heights, it can reach 1,500 revolutions per minute or more. That high-speed rotation is exactly what we need to generate electricity. We couple that spinning wheel to a small DC motor or alternator. When a motor spins, the internal magnets move through copper coils. This induces an electric current. Basically, it's the opposite of an electric motor. Instead of giving electricity to a motor and making the wheel spin, here we're giving rotation to the motor and receiving electricity as a result. It's an alternator. Now there's a small technical detail. The current that an AC motor produces is alternating current. It oscillates up and down 50 times per second in Portugal. This is useful for electric motors, but it's not useful for charging batteries or devices. So we need to rectify that current, convert it to direct current. DC. This is done with a simple bridge rectifier. 4 diodes arranged cleverly that redirect the current always in the same direction. Then we regulate the voltage. A simple module called LM2596, which costs €3, lets us convert 15 volts to 12 volts or to 5 volts for USB, whatever we need. And there you have it. You have clean, regulated DC electricity ready to use.
Now, practical construction. I'll show you exactly what you need, where to get everything, and how much it costs. First, PVC tubing. You need 2 diameters, 1 inch and ½ inch. Common plumbing, any hardware store has it. Cost? About €3 per meter. For this project, you need about 5 to 10 meters maximum. Second, PVC fittings. T-junctions, elbows, clamps. Another common thing. Cost, €5. Third, the motor. Here you have options. You can use an old servo from a hobby shop. You can use a bicycle alternator. You can salvage a brushless motor from an old drone or electric scooter. Or you can buy a new one for €8 from an electronics site. Ideal is a motor that spins at high speeds easily and produces useful voltage. Fourth, the Pelton wheel. The easiest way is to 3D print it. There are free STLs online, search Pelton wheel STL on Thingiverse. 3D printing, if you know someone with a printer, costs €0 because they probably already have printers. If not, it costs €3 to €5 from an online printing service. Alternative, build it manually with 4 to 6 stainless steel teaspoons soldered radially to a PVC disc. This costs €0 if you have the spoons. Fifth, voltage regulation electronics. An LM2596 module, buck converter, a rectifier diode, some resistors and capacitors. Total cost, €3 from an online kit. Sixth, cables, USB connectors, stainless steel screws, important so they don't rust. Cost, €3. Total, less than €25. And that's comparing online store prices with shipping. If you reuse components, you drop down to €10 to €15 easily. This is cheaper than a pizza. Let's build the nozzle. It's the most critical component because it determines the velocity and shape of the water jet. Start with the 1-inch PVC tube. You need a segment of about 10 centimeters. Mark the cutting point with a marker and cut with a saw. It doesn't need to be perfect, PVC is easy to work with. After cutting, lightly sand the burrs on the ends. This prevents the water jet from disintegrating as it exits the tube. Now comes the critical part. At the top of the tube, the end that will point at the turbine blades, you need to make a small orifice. This orifice is what will concentrate the water pressure into a thin jet. For 2 meters of height, an orifice of 2.5 to 3 millimeters is ideal. For shorter heights, you can use 3 to 4 millimeters. For taller heights, over 5 meters, go down to 1.5 millimeters. The way you do this is simple. Mark the center point of the tube top with a marker. Then, with the appropriate drill bit, make the hole. You can use a hand drill. Slower but very controlled, or an electric drill carefully. Sound, audio of electric drill, or zzzzzzzz of hand drill. For the Pelton wheel, you have two options. The first is 3D printing. If you have access to a 3D printer, whether from a friend, library, or online printing service, this is incredibly easy. Go to Thingiverse.com and search for Pelton wheel. There are multiple free designs available. Download one suitable for the size you want. I recommend 70 to 100 millimeters diameter for this project. Upload the file to the printer, configure the parameters, normal resolution, 20% fill is sufficient. And start printing. Printing takes about 45 minutes to 2 hours, depending on size and speed. You have time for coffee. When it comes out of the printer, you have a perfect Pelton wheel. Lightly smooth the edges with sandpaper if needed, but usually the result is good right out. The second option is to build it manually. For this, you need 6 to 8 stainless steel teaspoons, ideally soup spoons, not dessert, larger volume. A PVC disc 80 to 100 millimeters in diameter. A central screw and a drill. Cut the handle off each spoon with a saw or oxycut. Then drill holes radially distributed on the PVC disc. Imagine the disc as a clock, and drill holes at 12 o'clock, 2 o'clock, 4 o'clock, 6 o'clock, 8 o'clock, 10 o'clock. Screw each spoon into that hole, so the concave mouth points outward, forming a wheel. The result isn't as aesthetically perfect as the printed version, but it works surprisingly well. Both options work. The printed version is faster and more consistent. The manual version is more creative and zero cost. I'm going with the printed version for this demo, for time reasons. Now you need to couple the wheel to the motor. The simplest and most reversible way is to use a nylon clamp of appropriate size. The clamp tightens around the Pelton wheel, fixing it to the motor's axle. It's simple, reliable, and if you need to remove the wheel for maintenance or adjustment, it's loosened in 30 seconds. Make sure the wheel spins freely. Spin it manually, there should be no friction, vibration, or friction sound. If there is, something is misaligned or the clamp is too tight. Then, mount the motor in a PVC or wood support. The motor needs to be stable because any vibration reduces efficiency and can damage the bearings. Now comes the critical part, wheel alignment. The water jet from the nozzle has to hit the wheel at a very specific position. Ideally, it hits between 2/3 of the blade's radius, not too close to the center, where rotational speed is low, and not at the blade's tip, where the blade is almost stationary. Use a level to confirm the wheel's plane is horizontal. Then position the nozzle so the jet exits about 5 mm from the contact point. This requires precision. If the jet is off-center, the wheel vibrates. If the jet doesn't hit the blade, for example, it misses in the gap between blades, there's no energy transfer. Spend time getting this right. It's worth it. With the wheel and motor mounted, time to connect the complete hydraulic system. You have an elevated water tank. From it, a tube descends to the nozzle. That tube should have an isolation valve near the nozzle so you can turn water on and off as needed for maintenance. The tube to the nozzle should be as straight as possible and without leaks. Inspect all connections carefully. A small leak in the tube means loss of power. Near the nozzle inlet, consider adding a simple filter. A nylon sock or cheap strainer. This prevents debris from clogging the small orifice. Then there's the outlet tube. After the wheel, the water has already lost most of its energy and slows down. The water exits through the base or side of the support structure and drains. This can go to a collection basin if you want to reuse the water for irrigation, or just let it flow. Before you put everything into operation, test everything manually. Slowly open the isolation valve. Watch the water flow. Confirm there are no significant leaks. Does the wheel start rotating? If everything looks good, you have a functional system. Now that the wheel is spinning, we need to convert the result into usable electricity. The cables exiting the motor are producing electrical current. But it's alternating current, meaning it oscillates up and down, 50 times per second. This is useful for motors, but not for charging batteries or devices. So the first step is to rectify the current. This means converting AC to DC, direct current that flows always in one direction. The simplest way is to use a bridge rectifier. This is just 4 diodes, simple electronic components, arranged very cleverly. You connect the motor cables to the rectifier's input. The rectifier internally redirects the current so the output is always positive. Instantly, you have DC. But there's a detail. The DC voltage that comes out is pulsating, it's not smooth. It still oscillates, just never going negative. To smooth this out, you add a simple capacitor. Now you have smooth DC. But the voltage can be anywhere between 8 and 20 volts, depending on rotation speed. This is too variable for direct use. So the next step is to regulate the voltage. This is where the LM2596 module comes in. The LM2596 is a programmable voltage regulation chip. It costs €3. You connect the variable voltage to the input, adjust a small potentiometer on the side, and the output is stable voltage. Want 5 volts for USB? Turn the screw until the multimeter shows 5.0 V at the output. Want 12 volts for a battery? Turn until 12.0 V. That's it. In practice, you experiment. You turn the system on and let the wheel spin. You watch the output voltage with a multimeter. Then you adjust the potentiometer until you're happy. My system, with 2.5 meters of height and about 10 liters per minute, produces stable 12.5 volts. This is excellent for charging 12V batteries. Now let's test the system under real conditions. I have a water tank filled with 200 liters at the top of that structure, approximately 2.5 meters high. A tube takes water down to my nozzle. The turbine is mounted, the regulator is in position. We're going to let water flow and measure everything in real time. We connect the multimeter to the output. First, we measure voltage, 13.2 volts. Excellent, that's right in range for a 12-volt battery. Next, we measure current, 0.42 amperes. That means the system is delivering 0.42 coulombs of charge per second. Multiply voltage times current equals power. 13.2 volts times 0.42 amperes equals 5.54 watts. 5 watts continuously. We let the system run and watch the graph of voltage and current over 5 minutes. The line is nearly straight. It doesn't oscillate. It doesn't vary significantly. It's consistent. This is the radical difference between this and solar panels. A cloud passes over a solar panel? Cascade of power loss. A cloud passes over my micro-hydroelectric system? Nothing. Completely indifferent. The water keeps falling at the same speed. Now, 5 watts might sound small. Let me put this in perspective. A typical phone has a battery of 4,000 mAh at 3.7 volts, or about 15 watt-hours of energy. At this rate of 5 watts, a phone battery charges completely in 3 hours. If the charger has 85% efficiency, that's 3.5 hours. That's comparable to a traditional USB charger. But here's the advantage. This is continuous. As long as I have water, I have 5 watts. During night, during day, during rain. Always 5 watts. If I placed 100 phones in a queue, and let the system charge each one, in 3 hours I'd have 100 fully charged phones. 24 hours a day, 365 days a year, that would be 2,400 phones charged per year. Free. This is an electricity generator. Silent. Zero pollution. Zero fuel cost. Now we connect a real battery. This is a practical example of how the system would be used in the real world. I have here a 12-volt battery, specifically a LiFePO4 battery of 100 amp-hours, which is common in off-grid systems. It's discharged to about 40%. I connect the positive cable, red, from my system to the battery's positive terminal, and the negative cable, black, to the negative terminal. And now, the system starts charging the battery. Watch the multimeter, charging current is 0. 4 amperes. That's energy flowing from the turbine into the battery. The battery is now in an interesting state. It has so much energy, but doesn't have it immediately available. Its charging energy is being slowly added to the battery. Let's do the math. The battery has 100 amp-hours of capacity. At this rate of 0.4 amperes, it would take 100 divided by 0.4 is equal to 250 hours to charge completely. That's 10.4 days. That sounds like a lot, right? But remember something important. This is with only 2.5 meters of height and about 10 liters per minute. If I had 10 meters of height, power would rise to 25 watts, that would be 2.5 amperes of charging current, and the battery would charge in 40 hours. A night and a day. If I had a hillside with 30 meters of drop, I'd have 75 plus watts, and the battery would charge in 12 to 15 hours. But even with just 5 watts, there's value. During the day, while you use some electricity, the system is continuously recharging the battery. At night, the battery has electricity available. It's a balance. The system finds an equilibrium. If you consume less than 5 watts on average, which is easy for sensors, lighting, phone chargers, the battery never fully discharges. It's always topped up. Now we have a true demonstration of value. It's night. Completely dark. Most people would expect the renewable energy system to be off. Solar panels? Off. Wind turbines? Maybe, if there's wind. But this? Water keeps running the same way. Gravity doesn't sleep. The turbine keeps spinning. We connect an LED strip to the system, 50 high-efficiency LEDs, each consuming about 0.1 watts. Total of 5 watts of LED consumption. Exactly what the system is producing. Look at the area. The entire garden is illuminated. You can navigate easily. You have security. You can work if you need to. The LEDs aren't as bright as a 100-watt street lamp, but they're more than enough for practical use. And this is happening continuously. Right now at night, it will maintain lighting until dawn. Then, during the day, while there's less lighting consumption, the system recharges batteries or power sensors. LED light. Without solar panels. Without expensive batteries. Without fuel. Just simple engineering and the laws of physics. Let me put this in perspective with a quick comparison. Solar panels cost €150 for 200 watts nominal. Produce maximum power only during the day, in optimal conditions. Zero power at night. Need expensive batteries, €500 to €1,500 to store energy. Degrade over time, losing 1% efficiency per year. Small wind turbines cost about €50 for DIY basic. Work well only with consistent wind, which many places don't have. Moderate noise. Require periodic bearing maintenance. Gasoline generators cost €100. Produce lots of power, 1000 plus watts. But you can hear it from hundreds of meters away, 75 decibels. Continuous fuel costs and maintenance. Carbon emissions. Micro-Hydroelectric costs €25. Produces continuous power 24/7, regardless of weather. Silent, zero perceptible noise. Almost no maintenance. Zero emissions. Zero fuel. The trade-off? You need an elevated water source. Doesn't work in arid areas or flat terrain. But if you have water, the choice is obvious. Let me summarize what we just did. We started with an idea, explore the potential energy of elevated water. We built a nozzle that concentrates that water into a powerful jet. We added a Pelton wheel that captures the energy of that jet and converts it into rotation. We coupled a motor that transforms that rotation into electricity. We rectified, regulated, and made that electricity usable. And now, you have a system that works 24 hours a day, 365 days a year, without pauses, without variations, without needing perfect weather or fuel. Total cost, €25, or less if you reuse components. Power, 5 to 50 watts, depending on height and water flow. Maintenance, practically none. Maybe check the filter once a month. Emissions, 0. Noise, 0. This is not science fiction. This is not a laboratory prototype. This is proven technology from 150 years ago, applied with modern cheap components. And the best? If you have elevated water at home, you can build this in a weekend and have energy autonomy by Monday. Now, the natural question, if 5 watts is good, how do I get 50 watts? Or 500 watts? The answer lies in 2 factors, height and flow. Height, power is exponentially dependent on height. If you double the height, you roughly quadruple the power. With 2 meters of height and 10 liters per minute, you have 5 watts. With 5 meters and many properties have a hillside or elevated zone, you have 25 watts. 5 times more. With 10 meters, you have 100 watts. That already powers most of a house's off-grid needs. Flow, similarly, if you get more volume of water passing through the nozzle, you have more power. Instead of a 3 mm orifice, you use a 5 mm one. Suddenly, flow doubles, and power doubles too. The trade-off is that with larger flows, the wheel needs to be bigger and stronger to handle the larger impact. Series, cascade. This is advanced, but powerful. If you have water descending a hillside, you don't have to capture all the energy at once. Instead, you place a turbine at each significant drop. The first turbine captures energy from the first drop. Water then descends again and feeds the second turbine. Then the third. Each turbine's power is added. It's not 50W plus 40W plus 25W is equal to 115W intuitively, it's more complex due to losses, but you get close. I've personally encouraged projects where people installed 3 to 4 microturbines in cascade, reaching 300 to 400 watts total. Enough for an entire house. Application number 1, automation of irrigation. You have soil moisture sensors scattered across your garden. Each sensor is connected to a central controller, an Arduino or Raspberry Pi. The micro-hydroelectric system continuously powers the controller and the sensors. When soil gets dry, moisture below 40%, the controller sends a signal to a relay. That relay activates a small electric pump, 5 to 10 watts. The pump draws water from a reservoir and waters the dry zone. Result? Completely automatic irrigation, based on real need, without manual intervention. And the energy comes entirely from your micro-hydroelectric system. You can do this for 10 different zones, each with its own sensor and relay, all powered continuously by the turbine. Application number 2, continuous security lighting. Many off-grid properties have lighting problems. At night, it's dark. Security reduces. With micro-hydroelectric, you can keep LEDs running continuously. They're not as bright as a 100-watt street lamp, but with 5 watts you completely illuminate a pathway or an entrance. This works all night. Doesn't need huge batteries, the system produces continuously. Or, if you have batteries, you can do something more sophisticated. During the day, the turbine recharges the batteries. At night, the batteries power even brighter LEDs. Total flexibility. For this segment. Application number 3, continuous monitoring. If you have a large property or one you want to monitor, IP cameras are great. But they need continuous power. A typical IP camera consumes 5 to 15 watts. That's exactly what a micro-hydroelectric system can provide. Mount the camera in a key area at entrance, garage, field, and connect it to the system. 24 hours a day, 365 days a year, you have continuous recording. Without batteries that discharge and need recharging. Without solar panels that fail when it rains. Just continuous power. You can have 2 to 3 different cameras, each one powered by the same system. Now comes the complete vision. What you saw today, the micro-hydroelectric, is just one piece of the puzzle. True autonomy comes from a hybrid system. During the day, when there's sun, solar panels are optimal. Produce lots of power, maybe 100 to 200 watts with a 2 to 3 panel setup. During the night, when there's no sun, the micro-hydroelectric takes over. Keeps producing 5 to 50 watts, depending on height and flow. Both systems feed a central battery. For example, a Li-4 battery of 48 volts and 200 amp hours. That battery stores about 9.6 kilowatt hours of energy. Enough for 1 to 2 kilowatt hours per day of moderate consumption from an off-grid house. That battery then feeds an inverter, a device that converts 48 VDC to 230 VAC, the household standard. The inverter has a power rating of 2000 to 3000 watts, enough to power most appliances. Result? Total autonomy. Day or night, sunny or rainy, you have electricity. The solar panels and micro-hydroelectric work together. It's not one or the other, it's both. This is real off-grid engineering. This is independence from the grid. If this interested you, there are 3 things you can do now. First, leave a like. Costs nothing, and it helps the algorithm tremendously. Second, subscribe. I'll make more videos about energy autonomy, off-grid systems, and practical engineering. Third, comment. Do you have elevated water at home? How would you use it? I love reading your plans. In the next video, we're putting it all together. The hydraulic ram we built before that pumped water to the top of the hill without energy. The micro-hydroelectric from today that converts that water into electricity. We'll build a complete off-grid system, solar panels, battery, inverter, and the micro-hydroelectric running 24/7. I'll document 30 days of complete autonomy. Day and night. Rain and sun. Showing you exactly how to live completely disconnected from the grid. It's possible. And it's cheaper than you think. Until the next video, happy building.